Steinhauer here. Welcome back. We are working our way through cosmological questions and specifically thinking about the Hubble law and its implications for our universe. One possible implication is that the Hubble law implies that we are at the center of the universe. Let's think about why that is for just a moment. Here we are, the Milky Way galaxy. I'll denote us by a little blue dot here. And what is the Hubble law? Well, the Hubble law is that every galaxy in the universe is moving away from us at some velocity, directly away from us. It doesn't matter what direction we look. There's a galaxy and it's moving away from us. And there's a galaxy and it's moving away from us. And not only that, the further away a galaxy is, the faster it's moving away from us. It sure looks like, doesn't it, that the universe, we are stationary in the center, and that everything is expanding out from us, right? That sort of seems to be the implication of the Hubble law. It doesn't feel like we're moving at all, and yet all the other galaxies are moving away from us. And not only that, the further away they are, the faster they're moving away from us. So are we the center of the universe? Let's do a quick demo to see if that's the case.
I've got two pictures here. Here's one of them. It is a overhead transparency where I have drawn in a bunch of galaxies. I've painted one of them green and one of them red, and pink, and blue, and a whole bunch of other little galaxies here in the meantime. And if I take the same picture, and I just hit the enlarge button on the copier by 10%. That's all the difference between these two pictures is one of them has been enlarged by 10%. And the cool thing is you can reproduce the Hubble law with this thing. Watch this. If I line up the central galaxy, there it is. Get it better lined up. There, look at that. That's better. You can see in this enlarged version of the universe from one to the other, you can see the Hubble law right here. So here we are in the center of this diagram, and you can see here's a galaxy and it's moving directly away from us, and here's a galaxy and it's moving directly away from us, and here's a galaxy that's moving directly away from us. All of these galaxies, you can see the two dots are the motions at one time and then another time when the universe has been enlarged by a factor of 10%. Not only that, you see the Hubble law. The further away a galaxy is from us, the faster away it's moving from us. Well, that's cool, but clearly we're special because we're here at the center, right? Wrong. What if I line up this blue galaxy instead of our galaxy? Well, look what happens. From the blue galaxy's vantage point, also, it looks like the Hubble law is a thing. All galaxies are moving away from the blue galaxy, and the further away you get from that blue galaxy, including us, the faster that galaxy is moving away from that blue galaxy. Everybody sees the Hubble law. It isn't that galaxies are hurtling through space at near or faster than the speed of light velocities. It is that space itself is expanding. Look, I've lined up the red one. The red one sees this, the red one here sees the Hubble law. Everybody, no matter where you are in the universe, sees the Hubble law. It isn't that galaxies are moving really fast through space. It is that space itself, someone's hitting the cosmic enlarge button on the universal copier and just making it all get bigger. That's what's really going on. And so, no, we're not the center of the universe. In fact, we don't think there is a center of the universe. Everybody, from everybody's vantage point, it looks like they are the center of the universe. So what exactly is expanding? If it's not that the universe and the galaxies are hurtling away from the Milky Way at really high speeds through space, what exactly is expanding? Well, this little animation, I think, does a decent job of explaining it. So there's two, when most people think, hey, the Big Bang, which is really what we're talking about. We're talking about a time in the universe's past when all those galaxies were very close together. They think of an explosion that happens in space and galaxies go hurtling through the universe. That's not, so that's this explanation for the Hubble law. That is not what is happening. Let's do the simulation 2. What is happening? It's simply that all those galaxies are staying fixed, or relatively fixed, on their particular grid point, but the grid point itself is just getting bigger and bigger and bigger. And so that's a huge difference. In one, all the matter, all the universe was empty except for one point, and then at t equals 0, everything starts expanding. That's not what we think happens. At t equals 0, the universe is full of galaxies, but it's much smaller in the sense that any scale difference between these two galaxies is much smaller. And as you play time forward, they just get further and further apart. The scales themselves get bigger, but galaxies themselves don't move through space on the scale very fast at all. Great. So the expansion rate appears to be the same everywhere in space, and the universe has no center and no edge as far as we can tell. How do you picture this? This is really difficult to sort of conceptualize, but here is one decent way to do it. Now, again, this is going to be, our universe is a three-dimensional thing, but our brains can't handle, again, things being curved on a three-dimensional scale. But let's imagine a two-dimensional universe, similar to what we imagined when we did our black hole talk. In this two-dimensional universe, let's say we're a three-dimensional being looking down on this two-dimensional universe. You've got, let's say, the surface of a balloon. Now, this is a curved three-dimensional surface. In fact, one that curves back on itself. But in this analogy, you could imagine the universe itself being the surface of this balloon. So it's possible that this is, in fact, the true shape of the universe. In fact, if you're a two-dimensional ant on this balloon and you start moving in one direction, this balloon has no center, the surface of the balloon has no center, and it has no edge. A two-dimensional ant on the surface of this balloon could go walk in one direction and simply come back to where that ant started from. And it's possible we live in a universe that's very similar to that, where if we got on a spaceship and went off forever in one direction, we would eventually come back to where we started from in some three-dimensional shape. But I digress. It's also possible that the universe is just an infinitely flat sheet of rubber. It's also possible, we'll talk about the shape of the universe later. I don't want to get into too much of that now. Let's assume, though, that the universe is two-dimensional and think about this balloon analogy, because I think it works pretty well. So I am going to now press play on this button, the play button, and it is going to simply inflate this balloon. And you've got 4 galaxies, A, B, C, and D, that are affixed to the surface of this balloon. From the galaxies, each of galaxies A, B, C, and D's perspective, they are not moving with respect to this balloon. They are all stationary. They are all staying put. But as the balloon expands and stretches, all of them seem to get further apart. A is getting further apart from B. There's more balloon space between A and B. There's more balloon space between B and C. There's more balloon space between C and D. Let's rewind this and play it again. And I want you to think about the Hubble law. I want you to think about the relative distances between A and B, A and C, and A and D. The same amount of space is being added between all of these, but from A's perspective, B is moving away from it at some velocity. In other words, the space between it's getting bigger. There's twice as much space between A and C, and so that space is expanding twice as much. There's 3 times as much between A and D, and so that is expanding even more. And so the further away these galaxies are from galaxy A, the faster they seem to be moving. You get the Hubble law just by taking a balloon, pasting some things to it, and inflating it. And this is what we think is really happening. It's not that these galaxies are moving on the balloon. It's that these galaxies are fixed to the balloon, and the balloon itself is expanding. That's what we say. The universe is expanding. It's not that the galaxies are just moving through space. It's that the balloon itself is getting bigger. And that's a very important distinction.
Okay, so let's go back and think about this radial velocities and the z factor one more time. Let's think about particularly that galaxy at z equals 11.1, that one that's the furthest, the largest redshift galaxy, the furthest galaxy that we've ever measured. So what is the radial velocity calculated for that galaxy? It's not hard to do. You can say VR equals z times c, and z is 11.1. And so this implies for a galaxy at z equals 11.1 that it's moving at more than 11 times the speed of light away from us, right? Any galaxy that has a z greater than 1, the implication is that the radial velocity of that galaxy is greater than the speed of light. Well, I've spent a lot of time this semester telling you that it's not possible to travel faster than the speed of light. How is it possible that a galaxy, an entire galaxy, can be moving not only close to the speed of light, but in fact faster than the speed of light? That shouldn't even be possible. Well, the answer is, again, that it's not that that galaxy is moving through space at any really large velocity rate. It's not. From its perspective, it seems to be fairly much at rest with respect to the cosmic standard of rest. Just like we seem like we're pretty much at rest relative to the cosmic standard of rest. It is, in fact, that space is expanding between us that makes it seem like that galaxy is moving away from us at greater than the speed of light. It is that the more space there is, the faster that galaxy seems to be moving. So the true answer is it's not possible to move through space faster than the speed of light. It is possible for space to expand to make the apparent velocity between two objects be greater than the speed of light. That's a big difference, and it is an important and subtle difference that you need to understand as we're talking about these velocities. This isn't a velocity through space. This is a result of the expansion of the universe, stretching the wavelengths to make it seem like objects are moving away from each other at faster than the speed of light.
So if galaxies are not really moving through space at high velocities, what causes their spectra to become redshifted? Why do they seem, again, seem like we're fairly close to at rest relative to some cosmic universal resting frame. Why is it that distant galaxies appear to be so redshifted? It's not really that we're moving through space. It's that space itself is expanding between us. Well, we can also understand that with an animation. Basically, what happens is as these photons, as these light particles travel through space, they have a wavelength, and that wavelength, as the universe stretches under them, stretches the wave. And the wavelength will get longer. The longer this photon travels through the universe, the more space gets stretched underneath it, the longer that wavelength actually gets. Here is, again, the balloon, and you've got a blue photon traveling through it. If this photon travels through the universe long enough, the universe stretches underneath it. Again, relative to one of these grid points, the same number of wavelengths are always there, but the grid points themselves are getting further apart. And so the wavelength, as measured by somebody who is not expanding with the universe, will in fact seem to be longer. The longer this photon travels through the universe in distance and in time, the larger the redshift will get. And this is why it can get shifted past what seems to be the speed of light, because and nothing's actually moving that fast. It's just the wavelength getting shifted underneath it.